Welcome. Today I will take you on a tour to the magic of the origin of the laser. We will see that the laser is a unique form of energy, unique in the ultimate sense of quality as we can describe it in the whole universe. This is a big word, but it's true up to the limit of Heisenberg's uncertainty principle. To start with, I would like to display to you the content of the presentation. To do so, we designed the following outline for this session. We will start with some examples on thermal light sources and lasers. Then we will look at the phenomenology of laser light and its thermal brother, so to say. To describe thermal radiation, we look at the Planck's law of blackbody radiation and look at the experimental setup, how to really do the experiment. Then we will come to an important point, which are the modes and the density of states in which light can appear. And finally, we will look at how to reduce these modes, these number of longitudinal and transverse modes, and come to an outlook. Examples for thermal light sources and lasers. You are very well familiar with the sun, which is a typical thermal radiator, but also light bulbs are a little different already, are LED lamps or flash tubes, fluorescent tubes. But the main characteristics are shown in the upper right schematics, where you can see that the source emits into all thinkable directions, so in the whole solid angle 4 pi, with all kinds of wavelengths indicated by these little different waves here. So if we focus a thermal source, we only get a very small fraction out of the full emitted range of energy. Other in the case of the laser, where we are able, and I will let you know how, to select only one of these modes, one of these forms in which the radiation is emitted in terms of wavelengths, so we will have basically only one wavelength, and direction, so basically we will have only one direction as a consequence. On the left you see a few examples on CO2 lasers, YAG lasers and diode lasers, which we will discuss differently in more detail. The consequence of selecting only one, as we say, mode out of this huge variety in a thermal case, in building a laser, we have the whole energy of the emitting body directly converted into one direction and more or less one wavelength. Looking in more detail at these specifications in thermal light, use the light bulb here, which we can turn on now, and as you know, many colors are emitted: red, white, green, blue, and in all kinds of direction the radiation is isotropic in the full solid angle. If you look at the spectrum emitted, and here's plotted the spectral intensity over the wavelengths, you will see that depending on the temperature, those are values for higher temperatures, those are values for lower temperatures, we have a maximum of emission at a relatively small wavelengths for high temperatures, decreasing with lower temperature to then maximum emission at higher wavelengths. This is already the Planck constant, the Planck curve, that we will discuss in a minute. This light is incoherent, needless to say. Other the laser, where we have the typical emission in one direction and with one color basically. The words basically and in principle only result from the fact that we live in the uncertainty limit of the Heisenberg uncertainty relation. And you see here bunches of energy emitted, and this is a display not to be taken too serious, but it already shows us the dualism of wave in light and particle in light. So somehow it's a continuous wave, yes, but this wave, this energy in this wave is quantized. H nu is the single quantum energy, and this is illustrated, demonstrated by these bunches of of 4 wave ends here in one package. Important, if you look at the spectrum in comparison to the thermal emission, now we have basically only one wavelength emitted in the laser. And the solid angle in which the emission is radiated is very small, and the radiation is, as I said, very narrow in bandwidth, in line width, and that is why it is very coherent. In the next couple of slides, we will take a closer look on the thermal radiation. The example is the sun, and the description is Planck's law. Max Planck, who received the Nobel Prize for his genius approach of quantizing light in energy quanta, and from this deriving a statistics which allowed him to describe the thermal spectrum very precisely. Before we get into a physical analogy of the thermal radiators, let me use the example of the sun. You see here a picture on top, and if you analyze what comes out of that in terms of radiation, you will find for the intensity, which is the watts per centimeter square, or in other words, the spectral energy flux density, which is a product of the spectral energy and the flux density. And you can see here the intensity per frequency interval is the spectral energy, which is h nu, the energy over a corresponding distribution, times the flux, in this case combined with the energy, the speed of light, and here the energy of states, which looks a little complicated, but we will take the time in a minute and derive this expression very explicitly, because the number of states, as I said earlier, is very relevant for the differentiation between thermal light and a laser. So the spectral intensity is in watts per square meter or square centimeter. The density of states per frequency interval is 8 pi nu square over c up to the third power, and this is the density of states at a frequency in a given frequency interval, delta nu. And the average occupation, the photon number of states with the frequency nu, that is this expression here, in a thermal equilibrium, is given by this distribution, which you see contains a lot of Boltzmann similarity, but it is called the Bose-Einstein distribution. To make an experiment, we take a hollow cavity in which the light can propagate, and it will be reflected, it will be absorbed, it will be in equilibrium with the matter, with its boundaries. And then we drill a little hole into this and look at the radiation which comes out of this thermal equilibrium hollow cavity. And we find that the intensity depends on the wavelengths emitted, or the frequency in this case. And it has, of course, for very small frequencies, no emission, and it would be strange if for large frequencies it would not asymptotically go to zero, because the energy under this curve is given by the integral over this graph. Now, the spectral density of states, as I said already, can be calculated. The spectral intensity is the average energy times the speed, the velocity of light, times the density of states, the energy flux density in watts per square meter. And the energy per state in the classical case would be, following the equipartition theorem, just a half Boltzmann constant times the temperature. Now, if you plug this in, you get a graph shown up here on the right. So it simply would increase with temperature, and that would mean that at large frequencies we would have increasing emission up to infinity, which of course cannot be. This is what is called the UV catastrophe, and of course this cannot be the theory to describe this experimentally obtained distribution of the spectral intensity. Now what does describe it is, as said before, if we insert and apply a quantized energy. So we now have energy quanta. Each quantum has an energy of h times nu, where h is Planck's constant. And this hypothesis of an energy per state being a product of the energy of that quantum, that individual quantum, times the probability of occupation, which is given by this expression here, that describes the experimental behavior perfectly. Well, up to here this was pretty theoretical in terms of the modes. Now let's take a close, very practical look where these modes come from and how we come to this mathematical formula, proportionality to nu square, as you saw before. So, if again you recall, we have a cavity, and in this cavity we pick out one dimension only to start with. Later on we will extend it to 3. Then the resonance of electromagnetic waves can be seen very easily. We have, due to the Maxwell boundary conditions in reflection, the necessity that the electrical field is 0 at the point of reflection. So we have half a lambda, 1 lambda, 3/2 of a lambda, and so on, which fit in this cavity. So if you put this not in the words of wavelengths, but in frequency, with the simple equation that the product of the wavelengths and the frequency equals the speed of light, then we can look at the allowed frequencies, which just come up as the ratio of the speed of light over the allowed wavelengths. And this is proportional to a constant c over 2L, where L is the length of the cavity, times Q, the number, the quantum number of this state. So in frequency space, the individual states are equidistant. They have the same distance, and this distance just equals c over 2L. So one rather important fact at this point is that in wavelength space, the allowed wavelengths, of course, are not equidistant. 1/2, 1/3, 1/4, 1/5, 1/6, and so on is not equidistant. But in the frequency space, those differences are equivalent between allowed frequencies, and the value is just c over 2L. Now let's make an example to get some physical data. If we have a length of a cavity of 1 meter, a wavelength, I chose the wavelength of 10.6 micron for a CO2 laser, and the speed of light, we get as a mode number about 2 times 10 to the 5, so about 10 to the 5 modes fit into this cavity. A frequency spacing is about 1 times 10 to the 8 hertz. And the frequency is 3 times 10 to the 13 hertz. Just to give you a feeling on the order of magnitude. In a one-dimensional system, again, as I said, you can see it here plotted again on this vertical axis. We have a constant spacing of the individual modes. Plotted here is not the frequency nu, but 1 over the wavelengths, which is the wave number k in the wave space, in the k space. And if we go on and now look at the wave numbers in the 3 dimensions, so we go now from 1 dimension to 3 dimensions, we can simply denominate them by x, y, and z, and the k vector itself in total will be the sum of the squares of the individual participations. Now the volume in k-space is simply pi to the 3/3 power over v, the volume. Those are the modes, as I said, equidistant in k-space. And the density of states in k-space simply is 1 over the volume, which is the product of the lengths in the 3 directions over pi to the third power. It's plotted here on the right hand side. Here you can see kx, ky and kz. So here the 1, 1, 1 mode, x1, y1, z1 would be right here. Another mode is displayed up here, which would be the mode n2, 11. So we have 2 in y direction, n in x direction, and 11 in z direction. So the final wave vector k can be displayed and be put together by the contributions in x, y, and z and the individual quantum numbers to give the final state, in this case described by the 3 base contributions from x, y, and z. In the next step, we would like to calculate the total number of allowed state in a given geometrical limit. Think of a resonator, as we had the example of 1 meter in length, where we calculated the numbers. So now we have the Cartesian space of the wave numbers and integrate a spherical distribution of states up to a certain wave number value. If we do that, we simply get the integral over the density of states over the 3 dimensions up to the upper value, k prime, to which we want to count the states. We take only 1/8 of that value because we have redundancy in plus and minus and in x, y, and in z. So that's a factor of 2 times 2 times 2. And then we have only 1/8 of that full volume. However, we also include a number of 2 because we have 2 possible directions of polarization for each state. So that gives us then the full number of states possible in this corresponding volume. If we calculate this, plug in all the values from the previous graphs, we get this expression here for the number of states allowed, and already you see it looks almost like what we had in Planck's formula. If we now not only ask for the full number of states but for the density, we have to divide the full number over the volume, and this is very simple because then this Lx, Ly, Lz cancels out and we just are left with this expression. And now if we look at the spectral density of the states, that means the number of states at a certain frequency per frequency interval. Then we take the derivative, and that is shown here, the dn by d nu, and this deviation leads to the famous expression 8 pi nu square over c to the third power. So again, let's take a look at the full equation of Max Planck, which is again listed here in the upper left corner. And again, now you much better understand the expression on the density of states. You may not recognize it immediately because now it is expressed in wavelengths instead of frequencies. You know, it is physically the same, and we did that to let you know that people use both notations, some plotted versus the frequency, some plotted versus the wavelengths, because as you see on the lower right picture, plotting against the wavelengths is a little more experimentally reasonable because a wavelength is pretty easy to imagine. It's just a dimension, and a half micron wavelength just is a half a micron of a wavelength. However, 10 to the 15 hertz is very difficult to imagine, so that's why people use both notations. As you remember, the advantage of the frequency notation is the equidistant behavior in k-space. That is, or in frequency space. That is the point. Now, coming back to these pictures and looking at the behavior with respect to the temperature, we realize in increasing the temperature that the wavelengths of maximum emission goes to lower wavelengths, as we said in the very beginning as well. And you see blue, for instance, the wavelengths here at a cold emission at 250 K, in green, a little warmer, and 350K in red. So if you calculate all this, you get corresponding peak wavelengths, and there's a very simple relation between the temperature and the corresponding wavelengths of maximum emission in Planck's equation, and that is the Wien's displacement law. You see it here. The maximum emission just scales with 1 over the temperature with a proportionality factor taking into account Planck's constant, speed of light, and Boltzmann's constant. We can also derive another property from this Planck equation, and that is the total emitted energy. How do we do that? Well, we integrate just over the whole Planck equation. In this case, displayed over the frequency, and if you integrate over the whole curve, then as a result we get the total emitted intensity for all wavelengths, and if we again integrate this over the area, we get the total emitted power, which is then just proportional to the 4th power of the temperature. So that is an important result as well, that in hot bodies there is much more loss by heat radiation in comparison to cold bodies. It scales with the 4th power of the temperature. Now, in the next couple of slides, we will go into the physical details. I will show you examples, the physical laws, and the connection and the main difference in terms of the number of states light can take. And it's probably obvious already that in a thermal emitter, the number of states will be very, very large, and that in a laser, the number of states possible will be very, very small, in the limit just 1. To begin with, we look at a quantitative comparison between a thermal radiator, the sun, and a helium-neon laser. And we look at the photons per mode, and as expected, in the sun, we calculate for each mode 5 times 10 to the minus 2 photons per mode at a maximum emission of the wavelengths at about 500 nanometers. That corresponds to a temperature of about 5000 Kelvin. And in this case, we have very many modes, and each of these modes, of course, then is occupied by very, very little photons. In the helium-neon laser, in the limit, we have only 1 mode, and all photons are in this mode, and at given corresponding powers, we come up with about 10 to the 15 photons in this single mode of the helium-neon laser. So this is actually the thrilling result in difference, because in the one case, we hardly have any photon in a mode. The probability is only 1% or a few percent to have one. And in the laser, we manage to have all the photons in just 1 mode, and that is for comparable powers and energies a number of about 10 to the 15 photons. How do we select now these modes, these states in which the electric field can appear? And there are 2 ways to select them. Number 1 is the frequency, and number 2 is the direction. Remember the very first picture with the difference of a thermal radiator and a laser. So if we look at again at the frequency spectrum allowed in a hollow cavity, you remember in frequency space they are equidistant. C over 2L is the distance. And now if we place a medium which amplifies only a certain small range of photons, we are able to select only 1 or 2 of these modes to radiate at a time. So in this case, the selection of longitudinal modes, of frequency-spaced modes, just by choosing the corresponding active medium. The transverse modes, so the selection in direction, now is done by a resonator. it is displayed here in this picture. We have our radiating medium, and now we place two mirrors and select only one direction in which the resonance condition is fulfilled, so that all other directions are not allowed to realize. So we will have only in one direction the build-up of the radiation field and thus the emission of the radiation in the form of a laser. As an outlook, I would just like to show in the last picture two aspects in which we can measure quantitatively in longitudinal modes, so that was the different wavelengths, the frequencies, and in transversal modes, this is the direction of emission, the quality of the radiation. And this is maybe known by some of you already. For temporal coherence, we use a Michelson interferometer setup in which we can measure directly the line widths of the radiation. And you remember, the smaller the line widths, the less modes we have longitudinally in the system. And so the higher is the quality of the laser. And we do this by interference of the laser with itself with a certain displacement, and put together this interference picture here. The next outlook is then on the spatial coherence, and for that we do a very similar superposition experiment in terms of interference. Now we use two sources which we separate and measure the appearance of the interference spectrum. When it vanishes, we don't have enough spatial coherence, so that is Young's double-slit experiment. So these classical, pretty well-known experiments are really the quantitative pathways to analyze the quality between a thermal radiator and a laser, and ultimately it is the number of states which determines this quality. In the limit, for the thermal radiator, the number of states is infinite, and for a laser, it is 1.